Hello, everyone, and welcome to Effective Machine Learning with Cloud TPUs. I'm delighted to see all of you here, and I'd like to send a special welcome to everyone on the live stream or anyone who's watching this as a recording later. I'm Zak Stone. I'm the product manager for TensorFlow and Cloud TPUs on the Google Brain team, and this talk is about supercomputers for machine learning that are built around Google's custom chips called Tensor Processing Units, or TPUs. We've had 3 generations of Tensor Processing Units, including the one on the bottom that Sundar announced in his keynote earlier this morning. But before I get into the details here, I just want to set the stage for a moment and share a little bit of context about why this matters. There's been a tremendous amount of machine learning progress over the past several years, as you've already heard earlier today. If you look at the number of research publications on Arxiv, which is an open site for sharing papers, the number of papers published is growing faster than Moore's Law, and we're up to something like 50 new machine learning papers every day. This is a tremendous rate of innovation. A lot of it's happening in the open, which is fantastic, and it's driving a lot of new applications and real progress across a wide range of fields. As you can see here in just one domain, computer vision, there's been a tremendous increase in accuracy on this ImageNet benchmark challenge just over the past few years, rising from the original breakthrough results with AlexNet all the way to some of the more recent machine learning models. But these accuracy trends come at a cost that I'll tell you about in a minute. First, I want to help you understand what those sort of applications are about. You've heard a little bit about diabetic retinopathy and also these new signals of heart health that you can get in a completely passive way just by taking a picture of the back of the eye. This is the kind of real-world application that's going to help improve people's lives that's only possible because of these cutting-edge, accurate, powerful models in machine learning. You've also probably heard about tracking illegal logging in the rainforest by putting recycled cell phones in trees that can listen for sounds of chainsaws or other activities and help people protect rainforests in the central Amazon. Now, one thing that's really changed, even since I was in graduate school, is this unification across many different application domains. Before, it might have been that the folks in computer vision had one set of techniques, the folks in speech recognition had a different set of techniques, and the folks doing machine translation were doing yet a third set of techniques to go from, one language to another. But what we've been seeing over the past few years is this consolidation, especially in deep learning, around these neural networks that have similar components, even if the details of their structure are different. And these neural networks are now achieving state-of-the-art results across all these different tasks. Often these results are at accuracies that we don't know how to achieve any other way. So now, as I mentioned earlier, this has come at a bit of a cost, which is, as these models get more accurate, they tend to be larger, trained on larger data sets, and that means that you need more computation, both to train the model on the data set and then eventually to run it. What I'm showing here is this plot of these image recognition models on ImageNet, this time ranked with accuracy on the vertical axis, and then the number of multiply adds, which is sort of a rough metric of computational cost on the horizontal axis. And as you can see, as you get to these higher and higher accuracies, you're actually requiring larger and larger amounts of computation. So the solution to this problem, we believe, is specialized hardware for machine learning. And that's what's really driven us to develop these multiple generations of Tensor Processing Units, or TPUs. Our first TPUs have been in our data center since 2015, and you've interacted with these every time you've run a search. They're re-ranking the last several hundred links to choose the 10 that they're showing you. They've been a central part of Google Photos and speech recognition and many of Google's large-scale applications that you use every day. Last year, we revealed our second generation Tensor Processing Units, which are now in public beta. Anyone can sign up. Any GCP project can start a Cloud TPU, and you can follow the link g.co/cloudtpu to learn more. These TPUs aren't just for training and inference on a single system, though. They're really designed to be connected together into these large-scale supercomputers that we call TPU Pods. And later this year, TPU Pods are coming to cloud as Cloud TPU Pods. Here's a full pod of the second-generation TPUs on the screen right now. Finally, this morning, you're getting the first glimpse of our third-generation TPUs assembled into an even larger TPU pod that delivers more than 100 petaflops of compute for a single machine learning problem. So I just want to emphasize that we are committed to making relentless progress in this domain. This affects all of our products. It improves the lives of all of our users. And through the cloud, we're bringing these platforms to you so you can train machine learning models and run them faster and more cost-effectively than ever before. Just a few notes on performance. You can see TPU v1 with 92 teraops only doing inference, then going to the Cloud TPU, which is 180 teraflops. Suddenly you have floating point. It's a lot easier to work with. You don't have to worry about quantization. And those are connected together into these systems that, as I mentioned before, are up to 11.5 petaflops and do training and inference, either on a single problem or you can slice them into smaller pieces to do many different problems at once. Just a year later now, we're making this leap from about 11.5 petaflops to more than 100. That's more than 8x the performance of a TPU v2 pod in this new v3 system. And that's a combination of an entirely new chip wired together into an even larger scale system. So I hope the reason that you're all here is because you're interested in expanding the AI frontier. That's what really motivates us when we're developing these platforms and building applications on top of them. Now, I'd really like to focus on what you can do right now with the Cloud TPUs that are available today. And that really starts with performance. A lot of these machine learning models can take days or weeks to train. It hasn't been uncommon in the past for it to cost thousands of dollars just to do one training run of these machine learning models. And we're really interested in bringing down those costs and making machine learning acceleration much more widely available. But when we're talking about performance, it's important to be very specific about what we mean, because it's quite subtle sometimes to compare one system to another. First of all, in all of our measurements, we try to focus on real-world data, time to accuracy, and cost. So let me tell you what I mean. When you're training a machine learning model and you're processing millions of images, it's convenient to look at how many samples a second you're processing as a measure of performance. But those samples per second numbers don't matter unless you ultimately get where you need to go, reach the correct final accuracy. And so what we're really looking to do is, yes, measure how fast the wheels are spinning on the car, but also make sure that the car gets to the right destination and crosses the finish line. So it's very important whenever you're considering building, buying, renting a machine learning system to make sure that you're asking about not only steps per second or samples per second, but also the training accuracy and the total time to accomplish the task that you really have in mind. We've also put in a lot of energy to try and make sure that all these ML benchmarks that we talk about are reproducible via open source. So almost all the numbers that I'm about to show you, either you can reproduce today by going to g.co/cloudtpu and renting a Cloud TPU, or they'll be open source soon, and so you'll be able to reproduce them on your own. You don't just have to take my word for it. Now, Stanford recently hosted a competition called DawnBench. I've got a screenshot of the website here. And DawnBench is the first public benchmark challenge that we've seen really measure performance and accuracy together, which we think was great. There was active participation from many different companies and individuals and research groups. And I'm happy to announce that Cloud TPUs and TPU pods did very well across several of the categories. So in the ImageNet training cost competition, we had the #1 DawnBench entry with a model called AmoebaNet-D. Now, this is a really interesting fusion of some of the work that we've been doing in research with these new hardware platforms, because AmoebaNet was an architecture that was actually evolved from scratch on TPUs. And then that model, not only if you train it longer, can get to state-of-the-art accuracy on ImageNet, but it can hit the target that DawnBench set of 93% in just 7.5 hours for under $50. This really makes this kind of state-of-the-art performance accessible to a much wider audience than it's ever been before. Now, another model that you may have heard of that's frequently benchmarked is ResNet 50. And so I just wanted to show a quick case study of ResNet 50 running with TensorFlow 1.8, which is our most recent version. We also submitted this to DawnBench, and it also reaches this accuracy of 93%, which is not, this is top 5 accuracy, that's not easy to do with ResNet. It's easy to fall just a little bit short, and you have to be very careful throughout the implementation to achieve that high accuracy while maintaining this incredible performance of more than 3250 images per second. Now, this took almost 9 hours to train for $59, but if you want to go faster, part of the reason that we designed these systems to be connected together is just by changing the batch size of the model. No code changes, no complicated thinking about distributed systems. We can run the same thing on half of one of these TPU pods to hit the same level of accuracy in just 30 minutes. So that's 9 hours down to 30 minutes. And these are the pods that are coming to cloud later this year. So you'll be able to run results like this on your own or train on other models with other data sets of your own. And if you eliminate the checkpoint overhead, which DawnBench didn't actually require us to measure, that's actually just 24 minutes. So what I'd like to mention, though, is the field is moving extremely fast. So just as an example, the third place entry for training cost on DawnBench was from a nonprofit organization called Fast.ai. And that entry came in at $72, but it included some really interesting ideas that weren't well known. One was this progressive scaling up of training images that enabled the model to move even faster in the earlier phases of training when it's just starting to figure out how to complete the task. And they also used a much more aggressive learning rate schedule that hadn't been widely used. The nice thing about Cloud TPUs, it was easy for us to make these open changes in our own model on Cloud TPU and unofficially rerun the experiment. And these two simple changes take our ResNet 50 training cost from $59 down to just $25 with today's on-demand pricing that you can get on Google Cloud. So there's an open source reference implementation available. We've built this into our bfloat 16 version of ResNet 50, and we'll have more to say about this soon. But kudos to Fast.ai for the great algorithmic improvements. And I'm just delighted as a researcher and practitioner and now product manager that so much of this progress is widely shared. So you might be wondering, well, what's the next benchmark challenge? DawnBench finished recently. Where do we go next to compare these very different systems of different sizes and scales and even different model architectures against one another if we need to make a decision about what to do when you want to accomplish a goal? Well, one new challenge that's been released recently is MLPerf. You can learn more about it at mlperf.org. There are a bunch of researchers from different top universities and also many companies coming together to try and define a new next-generation benchmark that's even more challenging than DawnBench and covers many more problem domains. The first deadline is going to be in July. This group is open to new collaborators and also planning to iterate on the definition of the benchmark to make sure that it really tracks where the field is going. So I think this is going to be really exciting later this year, and I encourage you to participate and check it out. And as I've mentioned before, I just want to provide a little bit more information about what you can do today with Cloud TPUs if you want to experience this kind of performance. We've got this set of reference models. I'll say more about them in a minute, but they're right there on GitHub/TensorFlow/TPU. And we've also got great documentation on the Cloud TPU website with the link below. But you don't have to remember the big links at the top. Just g.co/cloud/cloudtpu will take you where you need to go. So now I'd like to give you a sense of what it's like hands-on to use these Cloud TPUs. First of all, one thing that's a little different than other accelerators is that they're network attached. So what that means is you can choose a virtual machine of any size or shape. You can attach other accelerators to it if you want. It can be large. But you would generally start with a very tiny VM because this is really playing just a coordinating role. As few as 4 cores are often enough because all the real computational work is happening on the Cloud TPU. The nice thing about this setup is that Cloud TPU can be a single device, or it can be a slice of one of those pods. You don't have to worry about it. All that's handled for you. Furthermore, you don't have to worry about messing with drivers. You can just use these machine images that we provide. You program these Cloud TPUs with TensorFlow. Now, TensorFlow is the most popular open source framework for machine learning, one of the top projects on GitHub. And it's just taken off since it was open sourced in November of 2015. We're now up to something like 13 million downloads all around the world. TensorFlow supports many different kinds of machine learning and has many different components. When you're programming Cloud TPUs today, you'll focus on layers, estimators, the tf.data fast input pipelines, and then your code will be transformed behind the scenes by the XLA compiler to talk to the TPU. So estimators and layers really provide these flexible, high-level deep learning abstractions for TensorFlow that let you map a wide variety of different models to TPUs. Here's just a quick code sample of a convolutional neural network. And this is how you would write it with layers and estimators with some code elided. What you can see here is that you just have to make some minimal changes to map this over to the TPU. Changes in the optimizer and the estimator. And we're working over time to make these changes smaller and smaller so that it'll be really convenient for you to take TensorFlow code that runs on CPUs or GPUs, run it on TPUs, move back and forth wherever you need to take your code and train or run. One important bit of advice, though, that I'd like to just emphasize over and over. High-performance computing is hard on any platform. And these accelerators are so fast that you need to really put in a lot of energy to make sure that the whole system is balanced and that every part of it is performing as well as it possibly can. We've done a tremendous amount of this work for you with these reference models that I'm about to show you that we've got open source on GitHub. For example, here are 4 different categories of very different applications that are either supported today or are about to be open sourced for Cloud TPU. Over in the image recognition column, which is maybe best known, we've got AmoebaNet and ResNet 50, also bigger versions of it, Inception v2, v3, v4. But we can also do object detection with RetinaNet, which is another one of these recent state-of-the-art models, and I'll say more about that in a minute. Also, if you're interested in training a machine learning model and then deploying it at the edge on a phone or a robot or a drone or in a vehicle or somewhere else, you might want to train a smaller model with something like MobileNet or SqueezeNet, and Cloud TPUs support those as well. But we're not limited to just image recognition or object detection. TPUs can also do machine translation and language modeling, sentiment analysis, question answering, all with this state-of-the-art model architecture called Transformer that's very powerful and flexible. Turns out a version of Transformer can also perform fantastic speech recognition. And we've just recently open-sourced an example of speech recognition training on Cloud TPUs as part of the tensor-to-tensor framework. I'll tell you more about that in a minute. And finally, for those of you who are researchers out there and are at the cutting edge where you're generating images from scratch, over in the image generation category, we've got the image transformer and also DC GAN. So we've really got a huge range of applications that are not only possible to make work on the Cloud TPU, but they're working today with open source code that you can just download. It's a really easy way to get started. So for those of you who aren't as familiar with this domain, image classification is often taking these small images like this one and mapping that to a category like lion, whereas object detection is taking larger images and looking for many different objects in many different places in the image. The cool thing about our RetinaNet implementation is it lets you process quite large images, 896 by 896, trains to a very interesting accuracy on the COCO dataset, 37 average precision, in just 6 hours for $40. Machine translation, training on the WMT dataset, gets to a BLEU score of 28.6, which is very close to the state of the art. Again, in just 6.2 hours for $41. And these results are, changing all the time as we continue to optimize the platform, the implementations, and new research comes out, much of which at Google is conducted on these TPUs. Now, language modeling, you're trying to predict the next word. This is an important component of applications like Smart Reply. And again, you can take the language modeling, the LM1B, the 1 billion word data set, and train to a state-of-the-art perplexity of 28 in 74 hours for under $500. And I've mentioned Tensor-to-Tensor again below. That's this open source project built on top of TensorFlow that has some of the latest and greatest results for all of these sequence-to-sequence models. For speech recognition, we've got this model called ASR Transformer, which is training on Libre speech, again, to a really interesting word error rate. This is a fantastic way, if you have a large labeled speech data set, to just train your own near state-of-the-art speech recognition model from scratch in whatever language or accent you care about. And you can get to a reasonable accuracy for under $100. Finally, question answering here. With QANet, this is just the fast version that we use to win the question answering competition for Dawnbench. But there's a Stanford question and answer data set that takes a big chunk of text and then presents a question about some fact that you can infer from reading the text. So this machine learning model is actually looking at this whole paragraph of unstructured text, reading the question, and then pinpointing the answer. It's really impressive. It's really different from image recognition, and all this is possible on this sort of flexible, new, powerful platform for machine learning. Oh, I forgot I was going to tell you a little bit more about image generation. So the metric here is actually bits per dimension, and lower is better. State of the art is around 2.92 right now, but under 3 is really good. And you can get under 3 on this metric in 30 hours for under $200 if you're interested in exploring this state-of-the-art, cutting-edge image generation examples. All those images on the right were generated from scratch, just dreaming on the basis of a training set using this image transformer model. So again, why start with a reference model instead of just opening a code editor and starting from scratch? Well, these reference models are high performance, they're open source, they're cutting edge, often collecting input from researchers all across Alphabet. We continuously test them for performance and accuracy, which means that you don't have to worry that some subtle change in TensorFlow or some other part of the stack might reduce the accuracy without you realizing it. You can get up and running really quickly and then modify as needed because you have the code. It's yours on your infrastructure, and you can train and run on your own data. But you're perfectly welcome to do it the hard way. We have lots of detailed technical advice in our troubleshooting guide, and I'm not kidding that high-performance computing is hard, and any part of the system can become a bottleneck, but we totally encourage you to take the high-level layers and estimators APIs and build new models, and let us know what works for you. Just to give you a little bit of a sense of what makes high-performance computing so tricky, if you're training with slower hardware, you might find that you can overlap your input preprocessing with your training time, and so your accelerators are always saturated. But when the accelerators get a lot faster, what you find all of a sudden is that you're bottlenecked on the input processing, and your accelerators are sitting idle. And so, fortunately, we've provided a bunch of tools that are connected into TensorBoard, which is this great visualization framework associated with TensorFlow, to help you debug your performance, understand what's going on. Here I'm showing the steps per second and the loss. But we actually have this very detailed profiler that lets you go in and get op-by-op statistics on what's going on in your model. And we even have high-level recommendations. I don't know if you can read the red text, but it's telling you, in this case, your model is not input-bound, so you should spend more time on optimizing the step performance. In other cases, it'll tell you, you're blocked on input. Don't bother improving the speed of your model. You need a faster input pipeline, and that's where TF data can help. So we're really doing our best to present these tools for experts and all this documentation for experts, but also to make it really easy to get started with these reference models across this huge range of applications. Now, those of you who are used to training and running machine learning models under your desk, you might wonder, well, why should I jump to the cloud? That seems like a different platform. How do I think about that? The nice thing about training in the cloud is that you get access to all this top-notch infrastructure where you can mix and match the different components you need, like those custom VM shapes I was telling you about earlier. You can scale up and down quickly. You don't need to order hardware, maybe build a machine yourself, wait for months sometimes for hardware to arrive. You can just sign on today and scale up to hundreds of TPUs if you wish. There's great security all throughout Google Cloud. Google is state-of-the-art in security across the entire platform for enterprises that want cutting-edge machine learning hardware. And you're really able to reduce your capital expenditure. With this on-demand pricing, you're just paying only for what you use. You can train one of these models for $50 and then turn the Cloud TPU off, and you're not paying for it anymore, which is great. So just a few words from two of our customers for Cloud TPUs. 2 Sigma is a financial firm, and Lyft, this is their self-driving vehicle team. Both of them have had great experiences using Cloud TPUs to focus on building the models instead of worrying about these massive distributed clusters of other hardware and taking these models that used to train for days in some cases down to hours. And with these larger and larger pods, we're really trying to drive that to minutes. So let's go under the hood and talk in a little bit more detail about what's going on in the current generation of Cloud TPU. So first of all, the Cloud TPU actually includes a host with this accelerator, all behind the scenes, connected via PCI. Each Cloud TPU device has these 4 chips under the heat sinks here, and I'm going to zoom in on one of them. If you look at the Cloud TPU chip layout, you'll see that it's broken down into 2 cores that look like this. Now, these cores are really built around this systolic array, which is an old idea, but it's newly relevant in this age of machine learning, when so many of the computations really look like gigantic matrix multiplies. But we've also got a vector unit and a scalar unit, and in this case, it was 8 gigabytes of high bandwidth memory per core, and then there are 2 cores per chip. The new TPU v3 actually doubles the memory per chip, which is going to let you train even larger and more capable models. Focusing in on this matrix unit, this systolic array, one thing that's really interesting about it is that we're actually doing the multiplies with a new floating point format that's called bfloat16. I'll say more about that in a minute, but it really gives us this great performance for machine learning without a meaningful cost in accuracy. We're still accumulating in float32, though. So most of you are probably familiar with 32-bit floating point. As you can see here, the orange mantissa bits are all devoted to measuring these fine differences between numbers, which is really important if you're doing high-performance computing, detailed simulations, that kind of thing. But in machine learning, it turns out that the range is much more important. And these machine learning models are not super sensitive to these fine differences, by and large. So the IEEE standard for 16-bit floating point truncates both the exponent and the mantissa, as you can see here, and it really cuts down the range of numbers that you can express. One thing that we're finding with TensorFlow is if you're training with half-precision IEEE like this, you really have to pay attention, and you need to get an expert involved on a model-by-model basis to make sure that all of your numbers stay in the right range and don't overflow. And those techniques are difficult to apply in general across a wide range of models. With bfloat16, though, what we've done instead is saved a lot more bits for the exponent, which preserves the range. And so in many models, this is a drop-in replacement for float32, and it's supported seamlessly by our Cloud TPU hardware. So those ResNet 50 results that I was talking about earlier, those were achieved with bfloat16. And as you notice, we're still achieving that high 76% top 1 or 93% top 5 accuracy with a minimum of effort and special casing on a model-by-model basis. So here I'll show you a brief animation of the systolic array. In this slide, it's only 3 by 3, but imagine this is 128 by 128 to get a sense of how different this is from an ordinary central processing unit and how much parallelism there is, which is where we're getting this fantastic performance. So here you have data streaming in, and what's happening as the systolic array sort of beats on every step is you're getting great reuse of these intermediate results as the data is flowing through the systolic array and generating the outputs. So this is super high throughput for matrix multiplications, and it's tightly integrated with the other parts of our TPU that support all these other custom operations. And our XLA compiler also does a great job of taking high-level mathematical expressions and then mapping them down into this coordinated dance of low-level operations that gives this tremendous amount of speed. So where do we go from here? Well, first of all, I really want to emphasize something I haven't called out explicitly about scaling up. I think the days of single systems are irrelevant. They're over, because what you care about ultimately is how fast you get to your result, right? And so what we're trying to do with these Cloud TPUs and making them widely available in the cloud is giving you just a dial that you can turn where you do your prototyping on an inexpensive single device, and then you increase the batch size without doing any other code changes, and suddenly your training time is going down from hours to minutes. And so I'll show you 2 real measurements from our TPU systems in-house here to give you a sense of how that's possible. First of all, what I'm demonstrating here, if you look at these TPU devices, so the 2nd generation TPU Pod has 64 of these boards in it. And you can see linear scaling of images per second up and to the right here. And as you know, remember, if you hear images per second, it's like, but wait, what about the accuracy? You can check our downbench results. That 30-minute result also confirms that we can still get the high accuracy with this scale out. But what you can see is that our interconnect in this pod is so fast that you don't have to struggle the way you would with mixing and matching hardware on your own, whether on-premise or in the cloud. You can just turn this dial with no code changes and benefit from this super fast proprietary network. But there's a more subtle point here that's a mathematical issue, which is until recently, it hasn't been clear how to take these machine learning models and increase the batch size, which is how many of these images you're processing simultaneously, sort of in each step while you're training. There's been a huge amount of research energy on this recently, and there have been a lot of breakthroughs where we're now able to train effectively on much larger batch sizes from ever before. That's great news for scaling up with these TPU pods. Let me help you interpret this graph. What you see on the horizontal axis here is time, and then what you see on the vertical axis is accuracy. And so you might imagine, your first implementation on your Cloud TPU that you're renting today gets to, let's say, 76% accuracy on ResNet 50, and that takes a certain amount of time. That's that orange curve out there. But with no code changes, just by changing the batch size in the right way with the models that we've already open sourced, you can pull that time in as you're using larger and larger sections of the pod, until you get down to these 30-minute results or possibly even better. So we think this is an extremely promising research direction, and we're doing our best in all these reference implementations to make sure that it's immediately accessible to you. So once these pods become more widely available in cloud, then you'll be able to just transparently benefit from this large batch training. I'd love to live in a world where you can use an exaflop for a minute and then let it go and think for a while somebody else is using it and just swap back and forth. Now, here's another view of the full TPU v3 pod that Sundar showed you this morning. And we are doing everything that we can to push the boundaries of performance, and that's what's really led us to liquid cool this pod in comparison to everything that we've done previously that's air-cooled. If you want a cool close-up view, here it is, a close-up view of just one of the boards in that pod. It looks sort of like this, and you can see the tubing. Now those plates are on each one of these next-generation TPU v3 processors. So we're going to go to the largest batch sizes we can. We're publishing all this research that we're doing. We're open sourcing as much of it as we can on these Cloud TPU platforms that you can access today. And so we're really excited in going with you into this exciting AI frontier. You can get started right now with these high-performance reference models and tutorials. And please reach out to us. Let us know. We'd be really interested in hearing your feedback on the Cloud TPU platform of today. We'd love to know where you'd like it to go. We hope you enjoy trying all these different applications across image recognition and speech recognition and image generation and machine translation. And I'd be happy to take some of your questions offline after the talk. So thank you very much for listening. I've included some links here. Thanks again.